Okay, hello guys. So this video is going to quickly talk about two additional properties of solutions that we haven't really talked about. So far we've mentioned many properties of water and why water's two hydrogen bonding sites as well as low molecular weight with its high dipole-dipole interactions, it's going to be able to cause many properties such as universal solvent, ability to have low density, adhesion, cohesion, these sorts of properties. But we're also going to add on two more. But these are general properties for solutions. Doesn't have to be water, but solutions in general. These are called colligative properties. Colligative properties means that these are properties that change based on the number of solute of particles present in a solution, essentially saying that these properties change with the concentration of the solution. So now that we've actually learned molarity, a way to quantify concentration, as well as dilution, able to manipulate the concentration, we can really talk about these properties and what they are, and how difference in concentration is able to affect these properties. Now in this slide, I know there's listed four, but we're going to talk about two specifically: boiling point and freezing point. So it turns out that if you add in concentration, meaning if you increase concentration, the boiling point will increase. For example, if a water, just plain pure water, it will evaporate and boil at 100 degrees Celsius. If you add in salt, table salt, the boiling point temperature will increase, so that instead of 100 degrees Celsius, it may be 103 degrees Celsius. Same goes for the other extreme, freezing point. It's called freezing point depression, meaning if you add in salt to water, the freezing point will no longer be zero, but some negative temperature. This may be why, if you've ever made ice cream using salt and water, rock salt and water, this is why. When you add in the salt and it's dissolved into the water, the higher concentration lowers the freezing point so that the temperature of the water is not 0 degrees Celsius, but some negative temperature, helping you freeze your ice cream. So let's talk about why this happens. Well, first of all, we need to understand that molecules, once it's dissolved, doesn't just freeze. Right? We've seen this video before where the water molecules pull apart the ions in a solid ionic compound, such as salt. But it's not like they just sit there standing still once they've been pulled apart. Right? Water molecules are always in motion. So I have this simulation to kind of give you a visual of what's going on with the molecules inside a solution. So right now I've just added some solvent, so I'll reset it one more time, but I added some solvent. Pretend these blue dots are just water molecules. Right? We can make it transparent or opaque, doesn't matter. But these are just solvent molecules, and in this case we're going to use water as an example. Down here there's three parameters. We'll mess with these in a little bit, but this is viscosity, just how thick they are, meaning if it's high viscosity, I guess the numbers are backwards, but if you have high viscosity, it's not moving a lot, but low viscosity is moving a lot. You have the temperature, KT times temperature, so if you increase temperature, obviously it's going to move faster, and time step just how fast everything is going. Again, we'll manipulate these later to kind of see the effects that they have. But if we add in some solute, meaning we added some salt and it dissolved, right? They're not standing still. They're being bounced around and pushed around by all these water molecules. This is why reactions happen when we dissolve ionic compounds, right? Think of the lab that we did dissolving lead nitrate and potassium iodide in two separate beakers. We poured them together. The reason why all the solutes were able to interact with each other is because they're moving around in the solution, being pushed around by the water, right? So right now they're not moving too much, but if we add more solvent and we raise the values a little bit and increase the time, you'll see that these red dots will be moving about, being pushed around by all these water molecules. They're jiggling everything. They're being pushed around and bouncing around. Okay, once we increase the temperature a little bit. Right, so you see the motions, they're kind of completely random, right? You got all these water molecules moving around, and they're being bumped around, right? How I like to think about it is like a bumper car, right? You got these guys that want to just stay where they are, they want to go somewhere, but you have all these water molecules in their way, and which is pretty much like a bumper car, right? You got these bumper cars, you're trying to drive some area, but then some other guy comes in and just slams into you. And you have to change the direction, or else you can't go anywhere. You can fight each other, and nothing will happen. Right? Look at that guy. Side note: while looking for videos of bumper cars, I found a video of Japanese people riding bumper cars. Don't think that's what it was meant to do, but I mean, I guess super polite Japanese, just regular day driving around to work, I guess. Anyway, so these molecules, right, the solute molecules are being moved around. Now, how does this relate to the two properties we just talked about? Boiling point elevation and freezing point depression. Okay. So let's move on to this simulation that I found. Okay. So here I have a machine that's able to switch between hot and cold, and I have I guess we'll call this a beaker of water inside that we're going to be using as our test container. So we have some water in there. So I'm going to use water as a solvent. This will be true for all of these. So I'll provide the link below that you can play with it yourself. But let's just start with water. Okay. So if we have just water, pure water that is, the boiling point and freezing point of water should be 0 and 100 degrees Celsius. Right. So what if we add in, let's say, well, let's just see, right? Right now we dunked the container with water into the freezing cold bath, right? It's cold, so the temperature is going to drop. Now, what do you think will happen once it keeps dropping? Do you think it'll keep going negative or not? Notice how the temperature stops at 0. Yes, it's fluctuated a little bit, but that could be just issues of instrumentation. But once water's already solid, it's formed a crystal structure, right? It formed a crystal structure. There's no more place to go. That's what a solid is. It's already as low temperature as possible. So the temperature can't go any lower. Right? So that's what the freezing point is, where the temperature can't go any lower because it's in a solid state already. Let's reset this and let's still do water with 170 grams of water. Well, let's add in some salt. Let's add 5 grams of salt. Remember, I'm adding sodium chloride. So, as usual, you dunk it in, starting with room temperature, 25 degrees Celsius. It'll decrease. Right? You would think, okay, freezing point should be 0 degrees Celsius. So, getting close, maybe you should start slowing down. But as we see, then the measurement keeps going lower. Right? Well, what's going on? Well, if we click on the micro level reaction, notice how instead of just the water molecule is able to just go into the cube, I'll play it again, right? Notice how the water molecule bounced off that orange molecule, right? The orange molecule is a solute. Well, when it was making its way towards becoming a solid, becoming part of the structure, its way got blocked by the solutes. So rather than just being able to collect into a solid structure, the pathway was not available to it. He had to bounce off and then come back around to form the solid. That delay caused it to be taking a bit longer, a bit more lower temperature for the solid to form. So when we added in just 5 grams of salt to 170 grams of water, right? 170 grams is just 170 milliliters. So just a little bit of salt, that's like a couple tablespoons maybe. Or maybe 1 tablespoon, but it's lowered the freezing point by 1 degree Celsius. Right. If we reset again, what if we decreased the mass of our water to 100? Right? What happens to the concentration? Well, Hopefully you answered the concentration would go up, right? Remember, concentration is moles of solute over liters of our solvent or solution. Well, if our solution is 100 milliliters rather than 170, keeping the mass the same, our solute the same, obviously our concentration would go up. So now that we have more solute available compared to the amount of solvent, the water that's trying to freeze, what do you think will happen to its process of going to freezing? Right. Notice how the temperature is going down a lot faster, obviously because we have less water. But look at the temperature. It's -3 degrees Celsius now. Right. We have much more solute compared to water molecules, so there's much more people guarding the water molecules from being able to align and fit into the solid structure. So this kind of helps us explain why freezing point depression occurs. It's because all the water molecules trying to get into the solid locations in its solid structure is being prevented by all the solute rummaging around. Now let's talk about why the boiling point increases. So let's flip this to hot. Okay, let's reset. Flip this hot. Let's, have 0 solute in there. Let's start with 150 grams of water. Okay. As you put it in, temperatures at room temperature. Hopefully it doesn't go too long. But it's a normal temperature. The energy is getting into the water. The water molecule is having more energy, and eventually it's going to start turning to gas, where it's just going to start leaving the solution, right? It's going to go into the air. Okay. Well, same thing happens when we add in some salt. So add in 5 grams of salt. Okay. Again, because the boiling point, what's happening when you're boiling water, the molecules are leaving the surface level of the water, but if we have stuff in the way, they're not going to be able to do that. Right? You need a lot more energy, a lot higher temperature for the water to actually leave, because now there's things in the way. Right? Think of football. It's easy to go to the end field with no linebacks, but when they got the defense, you got a lot more energy put in to get past them. So here, the temperature of boiling point is 100.36. Right? It's a little bit higher. I won't say a lot, a little bit higher than 100. Okay. So we have molecules. When solutes are dissolved in, it's preventing water molecules from doing what it wants to be doing. So that prevents it from freezing at the right temperature or boiling at the right temperature. And again, this happens with all the solids. You can go and test it yourself. Again, we'll do it again with lower water or lower solvent, increasing the concentration. You should expect that the temperature should be rising to a little bit higher than 100.3 degrees Celsius. Okay. I'm surprised it didn't show us the micro level of... Oh, it does. Okay. So, right, we have all these solutes, orange solids in there. They can't leave, right? They're not water. They have a much higher boiling point. They need a lot more energy to leave. But the water molecules that are trying to leave, see that guy right there? That guy just got prevented. He just got blocked. So you need some more energy, and here it says 100.83 degrees Celsius. Okay. So these are the two additional properties in addition to other properties talked about. These are called colligative properties. They depend on the concentration of the solute in our solution. Right? The higher the concentration, the bigger the effect. And again, temperature goes boiling point elevation, meaning up, and freezing point depression, meaning go down. In addition to the two new properties, I do have some activities for you to do. This will be linked in the description below. But these are virtual labs, meaning you can do this on your computer. Now, you do need to run this on Firefox or Chrome with some add-ons added in there. If you use Internet Explorer, as it says on here, there is some errors. So again, this is a virtual lab. You can do labs without actually physically handling chemicals and cleaning glassware and all that stuff. Just right click and clear bench, right? This is right click and clear bench. That's it. That's your cleanup. Okay. So each of these virtual labs has a task for you to do. To find out the task, you click on the top right where it's the name of the lab. Here is dilution problem 1. If you click on it, this gives you the task at hand. It says, using the virtual laboratory, create a 0.025 molar solution of glucose by diluting 1 molar glucose solution located in the stockroom. Right. So here you have the stockroom, which gives you a list of all the things in a stockroom, which means your supplies. So we have this solution, right? To bring it out onto the workbench, you just click on it, left click. You can bring multiples if you want to. You can right click on these to bring more options. I clicked on 2, I just want to remove that one. So this says I have 100 milliliters of 1 molar glucose. Right? You should be able to do the calculations to find out how many grams and how many moles are in there. But on the left side, whenever you click on one of these containers, there will be information about the species inside the container. Now, it will always mention the H plus and OH minuses. You will not need to know this yet. We will get to this when we cover acids and bases, including the pH. Ignore those for now. The most important number is the molarity, right? It tells you the molarity of this solution. And remember, the problem is asking you to make a 0.025 molar solution, right? Which means that's lower, which means we need to dilute it. So your task at hand is to dilute this solution to 0.025. There's a couple ways of doing this, but you should follow the proper lab technique or your own solution, right? So do this lab. Your number here at the end, if you click on it, will tell me 0.025. So how you can confirm that you've done it and turn it into me is complete the reaction or complete the task. Click on the container. Show me that the glucose is at 0.025 molars concentration. It doesn't tell you a volume, so it could be any volume. And then take a screenshot of this screen so I can see that you've done it. Again, don't be sharing screenshots with your friends because I'll know that if 10 people have the same exact screenshot, it'll look suspicious, right? You can move everything around, so I shouldn't be seeing workbenches that look exactly the same. You may work together if you have friends, call them if you want to, but I expect this to be, try to have fun with it. Play around with the information. You can click on the stockroom, explore real quick, look at what's available. You can learn some of the names of glasswares and what they look like. You got tools, you got Bunsen burners. One thing I will mention about Bunsen burners, you would think that if you heat things up to boiling point temperature, you would evaporate the liquid. It turns out, no. You can't evaporate stuff in this lab, I guess. So the volume doesn't change. All it does is change the temperature. So that'll be useful in some labs, but not this one. We don't care about temperature and dilutions. So, right, as you see, 100 degrees Celsius, volume is not changing. So don't expect to be able to, evaporate liquids and collect the solids. So you have these materials. You have, do your best. I will have a couple posted for you. So I have a glucose dilution lab, acid dilution lab, Coca-Cola and sucrose lab. This is a little bit different. If you read the problem, it's asking you to find out what the concentration or how much sugar was put into this generic soda. But just read the problem. And then I have a challenge question for you. This is the challenge one. This is determining the concentration of an unknown silver nitrate solution. This one has at the bottom a place for you to actually put in your answer to check it. Right? So when you do it correctly, you check it, it's right. You can screenshot this and post it. This will be extra credit. I don't know where I'm going to put this extra credit yet, but if you do this and you get it right, and you show me that you've done it yourself, right? I don't want the workbench to look exactly the same as 10 other people, so make sure you do your own. Read the problem, right? But the title says it all. So think about it, right? This, relates to our limiting reaction that we kind of did a week ago. So play around with this. And that's it. If you have any questions, let me know. Link, comment down below. Peace.